Getting things set up here. Getting things set up. Hold on one second. We're gonna see capture window. We need. There we go. Okay, now we have that. Now we can squeeze that in over there. We've got a new setup. Got things. Getting things a little bit set up here. I think that's good. All right. So today we're going to talk about things. We're going to talk about things. Cross-site request forgery. This is a problem. It's a security concern. It essentially allows other people to steal data. And you don't want your applications or your sites to be leaking this information. This is where we need to all be aware when we're building applications to know that attackers can leverage how you've architected your application. And this is client-side application challenge, right? That's the client can leak information in such a way that can be stolen and can be sent off to other destinations. And this can happen in a lot of different ways. And we're going to talk about that here with cross-site request forgery. This is CSRF, is a confused deputy attack. Wait. Okay, we're already starting off with a link to needs to go and read more information. So we know that this is going to be dense. We know this will be dense for sure. Let's see here. All right, so a confused deputy problem. What is this? What even? I don't even. This is what is that? Confused deputy is a computer program that is tricked by another program with fewer privileges or less privileges or rights into misusing authority on the system. A specific type of privilege escalation. This confused deputy problem, often cited as an example why capability-based security is important. Okay, so that would be a way to get around that. It's just using capability-based systems. So it's a CSRF is a confused deputy attack where the attacker causes the browser to send requests to a target using the ambient authority of the user's cookies. So specifically in web development, in this case, is what we're talking about. With cookies, if it's gives that user access or permission to perform tasks, because they've signed into a system. So now we've dropped a cookie onto their browser, which is remembered as a session. So that way, every time that user makes a new request for more details or to submit, data form submission, then this cookie will go along with that form submission, giving a sort of like a check mark saying, oh, we know who you are. We've already validated you because we gave you this session. The problem is these cookies can be stolen. And if the cookie is stolen, then the attacker can impersonate that user, steal their information, or act on their behalf. So that's the problem. For example, attacker.example can serve the following HTML to a victim. All right, form action, example.com, send money. That sounds like a method we should be secure with. It's a post. And we've got two input fields. They're hidden. Name to amount, and this is $1 million to Filippo. And the browser will send a post request to send money using the victim's cookies. Essentially, all applications that use cookies for authentication need to protect against CSRF. Importantly, this is not about protecting against an attacker that can make an arbitrary requests, as an attacker doesn't know the user's cookies, right? They don't know the cookies, but about working with browsers to identify authenticated requests initiated from untrusted sources. Okay. All right, that's interesting. So if we've got to, let's keep going. Unlike cross-origin resource sharing cores, which is about sharing responses across origins, CSRF is about accepting state change requests, even if an attacker will not see the response. Okay. Getting into the weeds here. Defending against leaks is significantly more complex and nuanced, especially in the age of Spectre. What is Spectre? Spectre security concern. Concern. There we go. Let's see. What do we get here? Security vulnerability. Okay. Spectre security vulnerability. Yes, Wikipedia needs to advertise a lot. Okay. Spectre is one of the most speculative execution CPU vulnerabilities, which involves side channel attacks. These affect modern microprocessors that perform branch prediction. Oh, right. Okay. So in order to for CPUs to get faster and faster, they sort of compile instructions before they're needed, so applications can perform more quickly. But the good news is the CPU will do extra work at predicting that the code path that's being executed will need to run those instructions. However, not all of them are needed, and a lot of them are thrown away. So it's a lot of like wasted work. But it turns out, because that work is done ahead, the application gets a performance boost, even though you're wasting a lot of energy predicting that extra. So that's what Spectre is. It sort of finds a vulnerability in that. Why do browsers allow these requests in the first place? Like anything in the web and the platform, primarily for legacy reasons, that's how it used to work, and changing it breaks things. Okay. So that's why we have these vulnerabilities, because if we just made a fix for it, like straight off, and mandated your applications worked a certain way, that would break a lot of the internet today. So it's important that we iteratively add capabilities that become optional but highly recommended. Importantly, disabling these third-party cookies breaks important single sign-on flows. So in some cases, right, it breaks other security implementations. All CSRF solutions need to support a bypass mechanism for those rare exceptions. There are also complex intersections with cross-site tracking and privacy concerns, which are beyond the scope of this article. Okay, so we're not going to go too deep, but deep enough. We're going to go deep enough here. Same site versus same origin. Hold on. Wait. Why are we versing the same thing? Same site versus same site. I think that's a problem. That doesn't seem like that was intended, but maybe it is. Let's read to see what we're going. To protect against CSRF, it's important to first define what is a cross-site or a cross-origin request, and which should be allowed. Sometimes you need these things because you're on an existing domain, app.example.com, but you need to access or submit information to another domain. So you need to read data or you need to post data to another domain. Subdomains, are often considered secondary domains, and in this case, this is the example that they're citing, these subdomains. Depending on the definition, all are same site, but not same origin. Oh, interesting. Okay, so same site, these are all considered same site, but same origin is different, because I suppose in this case, the origin is this, but these are different origins. Well, I guess this is a different origin, but interesting. Wait. Oh, because of HTTP versus HTTPS. Ah, that one's tricky. They should have highlighted that or something in here because it was not obvious what was happening. It's tempting to declare the goal as ensuring requests are simply from the same site, but different origins in the same site can actually sit at a very different trust levels. For example, it might be much easier to get XSS into an old marketing blog than it is in an admin panel. That makes sense. XSS is cross-site scripting. I think that's what that is. That's what we're doing. The stark difference in trust, though, is between an HTTPS and an HTTP origin. Yeah, since a network attacker can serve anything it wants on the latter. Okay. Yeah, this is why you might have seen browsers, once you're on HTTPS, it won't let any additional, I suppose, I don't know if there's a way around it. There might be a way around it, but once, a browser hits HTTPS as the origin, it won't let you load anything from a non-secure origin. Or it will, but it will give you big warnings, something like that. This is sometimes referred to as MITM. What is mitten? Hold on, I've never heard of this one. Let's check this out really quick. What is mitten CSS? Men in the middle. Oh, of course. Okay. Yeah. Let's zoom in here so we can read through this really quick. A man in the middle attack can be used to facilitate a cross-site request forgery attack. In a man in the middle attacker, an attacker intercepts communication between the user and the server. Potentially, so if there's a proxy, you can have a proxy in the middle, especially when I guess it's non-HTTPS, potentially modifying the communication. Oh yeah, so the attacker intercepting your communication not only reads all the information but can manipulate the data as it passes through. If the attacker can intercept the user's legitimate requests, they might be able to manipulate or create malicious requests that are unknowingly sent to the server. The user won't ever know. You won't know. The manipulated or malicious request could then be used to carry out a CSRF attack where the attacker tricks the user to performing unauthorized actions. Yep, they can totally take it all. But really, it's just a special case of schemelessly same-site, cross-site origin CSRF attacks. There's a lot of acronyms going on here, isn't there? Some parts of the web platform apply to schemeful definitions of the same site. Okay, so schemeful, I guess it's HTTPS versus HTTP. The schemeful definition. These are not the same site. They're different. Cookies in general apply to the schemeless definition. So cookie can be stored in HTTP and HTTPS. So that's why it's dangerous, because then you can have man-in-the-middle attacks with unencrypted data that in the clear, you can give away your cookie. So there's a problem. There is a proposal to address this, origin-bound cookies. Okay, so a new kind of cookie, and specifically the lack of opt-out for schemeless binding, which subsumes. Well, see, you don't need cookies anymore. There's things in browsers called sessions, and you can use the sessions. They're different because it's data that's stored within as a local temporary database on your app, in your app or your website or your web browser. And your app, your JavaScript, can access the session data to then submit codes with like an authorization header. So instead of using cookies, you can use something like an authorization header, which is a little bit different because cookies are automatic and you don't have any control when they're sent or not. But with a session, you have full control in that case. Which subsumes earlier scheme-bound cookies proposal, which, however, hasn't shipped yet. All right, so we don't have scheme-bound cookies, which means scheme is HTTP versus HTTPS, which would bind a cookie to just one of those rather than both, because it can hit both at the same time. The same site cookie attribute used to apply the schemeless list definition HTTP equals HTTPS. Chrome changed that with schemeful same site in 2020, but Firefox and Safari have not implemented it. Okay, so you've got some danger zone. If you're running Firefox or Safari, you are at a slightly higher risk. Chrome, and I suppose maybe even Chromium, maybe Internet Explorer, that will be fine. I don't know. I don't know for sure, but at least Google Chrome, we're safe on. So security fetch site and the HTML fetch specifications in general apply to the same schema full definition. Okay, so HTTP is not HTTPS, and data will not be shared between the two. Using HTTP strict transport security, HSTS, if possible, is a potential mitigation for these issues. Yeah, I think this is one of my favorites, is to use strict transport security, which explains to the browser, communicated either in a header that's served with the document, or with metadata that's served inside the document, a meta tag, that forces the browser to enable this. And it says, be very careful. I want to make sure that we don't leak any information between HTTP and HTTPS requests. Because, right, the men in the middle, they can read clear text, no problem. Countermeasures. There are a number of potential countermeasures to the CSRF, some of which have been available only for a few years. Okay. Double submit or synchronized tokens. The classic countermeasure is CSRF token, a large random value submitted in the request as a hidden input and compared against the value stored in a cookie, sort of like double submit, or in a stateful server-side session, synchronized tokens. Interesting. Okay. I'm not familiar with this approach. I've seen it before and been confused by it. I've looked in source codes and seen like, what's going on here? That's kind of weird. Normally, double submit is not a same origin countermeasure because same site origins can set cookies on each other. Right, cookie tossing. I didn't know that was a term. So I guess you can buy, like, an application might intentionally bypass this by setting cookies on both HTTP and HTTPS. This can be mitigated with the host cookie prefix or by binding the token to the session of the user with assigned metadata. Okay. The former makes it impossible for the attacker to set the cookie, but the latter ensures the attacker doesn't know a valid value to set it to. Okay. So there's a lot of nuance here, and to be honest, I need an example. That's what I need to see a little bit further on the details on this. Note that the signing of the cookies or tokens is unnecessary and ineffectual unless it is binding in the token to the user. An attacker that's cookie tossing can otherwise obtain valid signed pair by logging into the website themselves and then use that for the attack. Okay, so we're not fully covered here. This countermeasure turns a cross-origin forgery problem into a cross-origin leak problem. If the attacker can obtain a token from a cross-site origin response, it can forge a valid request. The token in the HTML body should be masked as a countermeasure against the breach compression attack. There's so many attacks. This is the internet is insecure. We got to be careful. You got to be careful on the internet. Be very careful. The primary issue with CSRF tokens is that they require developers to instrument all their forms and all their post requests. See, that's one of the things with this is these extra sort of, conditional setups that you use with verification tokens and signatures. It's error prone for one. It's error prone. You can make accidents, and it can be problematic. So you just got to be careful. Browsers send the source of a request in the origin header. So CSRF can be mitigated by rejecting non-safe requests from the origins. I think now we're getting into a little bit of a better solution. The main issue is knowing the application's own origin. One option, obviously, is asking the developer to configure it, but that's friction and might not always be easy, such as for open source projects. Yeah. And this is problematic because you also have different environments where your web application's running. And if you're running your web application on a test environment, you're gonna have a different domain, maybe even different schema. If you're running it locally, you can't always know what that domain's gonna be. And if you have to set it manually within a header, you're gonna cause friction. Yeah, it's super secure, but now your application might not be able to work in different environments easily. The closest readily available approximation of the application's own origin is the host header. This has two issues. It may be different from the browser's origin if it is from a reverse proxy. Yep, that makes sense. It does not include the scheme. Okay, so you don't know if it's HP versus HPS. So we can't just interpolate. We cannot interpolate what the domain's going to be. Some older pre-2020 browsers don't send the origin header for post requests. Okay, so there's another reason. The value can be null in a variety of cases, such as due to the refer policy, no referrer, or following cross-origin redirects. Null must be treated as an indication of a cross-origin request. If we see null, some privacy extensions remove the origin header instead of setting it to null. This should be considered a security vulnerability as well, introduced by the extension, since it has removed any reliable indication of a browser's cross-origin request. So if we see that the host is missing, we can assume nefarious activities. Same site cookies, if authentication cookies are explicitly set with the same site attribute lax or strict, they will not be sent with non-safe cross-site requests. Okay. So if in this case, if we're setting it, but we don't set it for all the domains or all the requests, it will get blocked potentially. This is by design and not a cross-origin protection. It can be fixed with the host header prefix or secure attribute, since that's about who can set and read the cookies and not about where the request is originating. This is just, there's just too much. I tell you, there's just too much here. This is different. The difference is reflected in the difference between the schema-bound cookies and schema-full same site. The risk of same-site HTTP origin is still present as well in browsers that don't implement the schema-full. So I guess we have to be cautious when we're building our applications in these security considerations for older browsers. Though, how many? I guess it really depends on the application. If you need to support every possible user case, you're going to run into some issues on these security concerns. Though, even if you set it just means in some cases with some of these security designs that it's actually okay to implement the new security patterns that are only available in the newer browsers, because older browsers will run into some of these config settings, not even know what they're for, and just assume that it's application level logic and completely ignore it. So if you don't have an up-to-date browser, you're at risk. Though if you're in a new browser, you get the benefits of the security. That's actually the bonus there. So it doesn't break old computers or old browsers, but you get the advantage with the newer browser. Note that the rollout of same site lax by default has mostly failed due to widespread breakage, especially with SSS flows. Some browsers now default to lax, allowing unsafe, while others defaulted to none for the first 2 minutes after the cookie was set. Oh, neat. Okay. So it's implemented just to support SSO, but for the first 2 minutes, and then it triggers. That's kind of a neat workaround. I like that. That's pretty nifty. Defaults are not effective for CSRF countermeasures. Okay. Non-simple requests. Although CORS is not designed to protect against cross-site request forgery, non-simple requests, which for example set headers that from a simple form couldn't set, are pre-flighted by options requests. Let's check that out real quick. Although CORS is not designed to protect against CSRF, which is, for example, form, couldn't set pre-flight by options requests. An application could choose to allow only simple requests, but that is fairly limiting precisely because simple requests include all the ones produced by form. Okay. Interesting. All right. Well, we'll probably want to go through more of this here in a bit, but I do got to jump to a meeting. So we will pause here and we'll be back a little bit later to go over. I'm more interested in protecting against cores CSRF in 2025. That's going to be neat. We'll check that out here in a bit. But yeah, I will be back in a little bit. Well, some hours. I don't know how many hours, but a few hours. Maybe later today. That's the plan.